We have been looking at clock and data recovery circuits for a few weeks now, and we had two choices: a linear phase detector and a bang phase detector. Now, everything that we discussed so far, like jitter tolerance, jitter generation, jitter transfer, etc., all this analysis is the same for the two, except, of course, for the linear phase detector, the gain of the phase detector is 1 by 2 pi or ICP by 2 pi, right? Whereas for the bang phase detector, the gain itself depends on the input jitter. Okay. Now, we have not discussed this part of it. The input data, especially in longer channels, comes with some intersymbol interference because of the bandwidth limitation of the channel. So the data is bound to have some jitter. Okay, although I draw these rectangular waveforms with no jitter, the input data is bound to have some jitter, and that will sort of linearize the bang phase detector, as you have seen in the assignment, right? If you have no jitter at all, the gain is infinite. That is, just before or just early and just late clocks give you plus or minus 1. But if you do have some jitter, then you have a smooth transition between minus 1 and 1. Okay. Now, in all these things, you have the expression for the gain of the phase detector, KPD. Okay. And that the same analysis you can use for both linear and bang with the appropriate gain. Okay. Just change the value of KPD. Only thing is, for bang phase detector, you need to know what the input data looks like, and consequently what the jitter between the data and clock is that is entering the phase detector. Okay. So we looked at jitter tolerance, of course, and then jitter generation due to the resistor, the charge pump, and the VCO as well. Okay. The part due to the charge pump will be low pass. The part due to the resistor will be band pass, and due to VCO also the output spectral density will be band pass. Okay. Because the VCO has a low pass type spectral density for phase, and then that going through the high pass spectral transfer function gives you a band pass type spectral density, right? Because we saw that we have S by omega Z here. This is similar to what you would get from the resistor. Okay. Now this is not very surprising. We could have also done it in a probably easier way. I just showed you like this. Let's say this is a VCO with a gain kVCO hertz per volts. Okay. And let's say the output phase noise spectral density, some A by F square. Okay. Now exactly the same thing can be produced by, this is a noiseless VCO, and some noise voltage here. What does this noise voltage have to be, or what should be the spectral density of this noise voltage to get the same phase noise? Or what is the relationship between the spectral density of this Vn and the phase noise of the output? K square. What is the relationship between the control voltage here and the output phase? Yeah. What is the transfer function? 5 Vc of S by V control of S. What is it? No, in our notation, what is it? kVCO by S. 2 pi kVCO by S. Okay, because our kVCO is in hertz per volts. Okay. So what is the relationship between the spectral density of Vn and the output phase noise? It will be SVN of F times what? KVCO by F square. Okay, this will be S by of F. Now, depending on whether you take one or two-sided spectral density, this will be the same as L of F or 2 times L of F. Okay. So now what should be SVN to get a certain phase noise? Let's assume that this is the two-sided spectral density. Then this is the same as the phase noise spectral density, right? Meaning it will have both positive and negative parts. Only the phase noise will have only the positive frequency part of it. So it will be F by KVCO square times A by F square. Okay. So it will just be A by KVCO square. It will be some constant. Okay. It's very clear, right? If you have white spectral density at the input, you will get a 1 by F square spectral density, phase noise spectral density at the output. So the noise of the VCO can be equally represented by a white noise at the control input. Okay. Now remember, when we had a resistor noise which also adds to the control input, we had a band pass transfer function from there. So this whole thing is like this white noise going through a band pass transfer function. Is this okay? So all of these things can be calculated for the bandgang phase detector also with the appropriate KPD. Okay. Now we will discuss something else which is specific to the bandgang phase detector. Okay. Before we go there, any questions on any aspect of the CDR we have discussed so far? Now, to see what happens specifically in a with a bang phase detector, what we'll do is the following. We'll assume that the VCO is at the right reading frequency and analyze only the proportional path, because the instantaneous changes are only due to the voltage across the resistor. Okay. So we can essentially, another way to think about it is we will use an infinitely large C which will hold the right control value to get the VCO to the right frequency. Okay. So we can analyze only this part, that is, we will just ground this part of it and the capacitor is not there. Okay. We will assume steady state operation at the with the VCO being at the correct frequency. Okay. Now the exact same analysis applies if let's say if we were looking at the clock and data recovery with a forwarded clock. Okay. So in this case, we'll have only the capacitor. We know that the way this clock phase behaves here is exactly the same as the way it behaves in this case with the VCO being at the right frequency, right? In fact, we derived this from the other case. So whatever I say now will also apply to this. I will use the other one as example, but the same phenomenon will apply here. This is okay? So I'm going to consider only the proportional path because I'm only sort of looking at rapid or instantaneous changes. I'll assume that the VC of frequency does not have to be corrected. Essentially that's what it means, right? Or alternatively, you can think of it as analysis of the other case with the forwarded clock with a bang bang phase detector. Okay? So let me show only this part of it. The VCO is at the correct free running frequency. Okay? Now in this system, let me assume alternating data for simplicity in the beginning. This is the data input. And this is the clock, which I have shown as ideally being locked to the right position. Okay? So, what will up and down look like in this case? So we have up and down pulses here, right? What will they look like? Huh? 0.5? What's that? No, this is a bang bang phase detector. Does that ever happen? What will the up and down pulses look like in a bang bang phase detector? You will either get up or down for a full cycle, right? I mean, in every cycle you make a comparison. If the clock is early, you get a down pulse. If the clock is late, you get an up pulse. Okay? So, but what will that look like here? When you have alternating data, what do you think the up and down pulses will look like? Huh? Correct. On an average, of course, it should be 0. But what will the pattern be? Up, down, up, down. Okay. So, let's see. So, maybe here the clock is slightly late, so it is up. And then you are saying next time, because it is slightly late, it will pull it earlier. And then the next time, you will get a down pulse and an up pulse. The down pulse and so on. Okay. So we'll get alternating up and down pulses is the hypothesis. But let's see if this is possible. Okay. So this so this means that basically if I plot the phase of the clock, right, what will that look like? For these up and down signals, the phase of the clock will behave in some way. What will that look like? Please work it out. What is it? We have the model, right? We have the model for the VCO and everything. Huh? No, but what will be the shape of phi ck? Huh? Step? Why will it be step? Ramp. So when up signal is high, you will get, what will be the voltage here? What will be the voltage there? Plus ICPR. Okay. In response to that, what will be the phase of the VCO? Yeah, basically it will ramp up, and the slope of that will be 2 pi ICPR KVCO, right? Because what is this ICPR? This is the voltage here, and KVCO times ICPR is the frequency stepped. Okay, that is so right now when there is when both up and down are 0, this is oscillating at the right frequency. When you have up as high, you will have ICPR as the control voltage, and KVCO times IP times R, ICP times R as the frequency step. Okay. And with that frequency step, the phase will ramp like that. Okay. So it will be ramping up here, and it will be ramping down there, and ramping up there, down, and so on. Okay. And what is the peak to peak value of this ramp? Yeah, so it will be 2 pi ICPR KVCO times T naught, or whatever symbol we use, TS, okay, where this period, the data symbol period is T naught. Okay. Is this fine? Now this is a little involved, so just follow the details. Now what it means is that the clock phase is going up here. So that means that clock moves to the clock edge. Which way does it move from here to there? Does it move to the left or right? From here to there? It moves to the left. It becomes more leading, and from here to there it moves a little to the right, and so on. Okay. So now the phase of the data, or 0 must be here. Okay. We assume that the data has no jitter. Okay. So now essentially at this point clock is leading the data, here clock is lagging the data, etc., etc. Okay. Is this fine? That's what we have assumed. Let's see if this solution is really possible. Okay. Now how does the bang phase detector work? We'll consider 3 samples, right? The 2 successive data samples and the transition sample. And what is this actually measuring? It is measuring whether this falling edge is earlier or later than this data transition, right? Now where does that output come out? When does it come out? Actually, this up and down I drew it wrongly, right? This up and down will be aligned to the rising edge of the clock, the way we have made the bang detector. So, but that's okay. All I have to do is maybe just move this whole thing over by a clock cycle. Okay. So up and down will be aligned to the rising edge of the clock, right? Aligned to the data sample. That's how we have made this. So here also the same thing. Okay. So now, where do we get the information for this particular transition, whether the clock is early or not? Where are we getting that? This one. So these signals, the up and down signals here, correspond to that one, right? And in fact, the waveform will be delayed a little more because of clock to Q delays. Okay, if there's a clock to Q delay is 0, it will look like this, but it will actually be delayed a little bit more. Okay. So uh, now looking at that, can you tell me if this kind of a solution is possible? So let me move this a little bit more to make it clearer. I'll move it slightly. Okay, personally I can't do that here. So I'll do it like that. Okay. So if what we have written here is correct, at this point the clock is too early, right? That is why we are getting a down sample over there. Okay. But if you look at this here, the clock is not early, isn't it? Meaning the response here depends on the phase about half a cycle before, maybe a little bit more than that. Okay. So that means that if you are getting an up signal here, so if you are getting a down signal here, the clock should have been early over there. Okay. Is this part clear? So similarly, the solution is saying that if you are getting an up signal here, it should have been late at that point. But if you look at the way the phase is drawn, that's not quite right. In fact, it is slightly early. Okay. So in fact, this solution is not quite possible. Okay. This alternating up and down, we assume that, we knew that the average had to be 0, and we assume that, of course, we also know that the clock goes between being a little too early to being a little too late. But it cannot be alternating in every cycle because there is delay in this phase measurement. Okay. So if you have an up, if this clock edge is too early, you don't get that information immediately. Okay. So you don't get the down signal or this down ramp of the phase immediately. Okay. So just think about it. So what could be the solution? First of all, are you convinced that this cannot be the solution? There is delay in measurement, right? Because we are measuring this clock edge here, and the result of that is coming half a cycle later, at least half a cycle later, maybe a little bit more than that. Okay. So that means that if you have this single symbol alternating, I mean if you have up and down alternating every symbol, so that means that if it was if it is showing down here, clock should have been early about half a cycle before, maybe a little more than half cycle before. Okay. But it doesn't seem to be possible. If up and down are alternating in every cycle, that's not possible, right? Is this okay? I mean, is this clear or not? Okay. So then what will be the solution actually? If you have alternating data to a CDR with a back-bank phase detector, how does it lock? Huh? I mean, what? So basically you get 2 ups and 2 downs and so on, right? That's what should happen. Anyway, you think about it, you can draw the phases and think about that one. So this we said is not possible. Now we'll see, because of the delay perhaps we'll get two consecutive ups and two consecutive downs and so on. And again, as usual, it will be a little bit delayed compared to this. Maybe I'll show a slightly greater delay for clarity of drawing. So I'll show it here, slightly delayed from that one. Okay. Okay. So now what happens to 5VCO? It will ramp up, but the peak to peak will be twice as long. Okay. The slope will be the same. It will be that ICPR KVCO will be the frequency step. 2 pi CPR KVCO, that will be the slope, right? Now, is this a feasible solution? What do you think? So now this is the phase of the data, which is 0, right? Okay. Now essentially the way to check it is the following. In this 5VCO waveform itself you can check. If 5VCO greater than 0, this means that, so here clock is leading or too early, and if 5VCO is less than 0, because we have considered 5D to be 0, right? Ideal periodic data. So this here, the clock is lagging. Also, if the phase is rising, it means that you are getting an up signal. If the phase is falling, you are getting a down signal. Okay. So all you have to do is, at every point, essentially you have to check whether a little more than half a cycle ago, it gives you a consistent waveform. Okay. Is this okay? So now that means that so let's say delay is maybe just for the sake of writing it, I will show it as approximately like I'll show it here. Let me show this. This is the delay. I have shown it as approximate, I mean something more than half a cycle, maybe 3/4 of a cycle. Okay. So this is where you have an up, and this is in response to, maybe let me write it like this. This one is in response to a phase over there. Oh sorry, this is where you have it down. I mean, let me correct this. So in this period, you have down, and this is in response to something that happened a little more than half a cycle ago. So that seems fine. A little more than half a cycle ago, the clock was leading, clock was too early, so you get a down. Okay. And similarly, this is another down signal, and this happens little more than half a cycle before that. Again the clock is leading. Okay. And here I have an up signal, and this is in response to something that happened more than half cycle back. So clock is lagging, so you get an up. Okay. And here so again you will look at something that happened little more than half a cycle ago. Again the clock was lagging, so you get an up. Okay. So this may be, I mean, this is something important to know, because if you just set up the simulation and do it with alternating data, you will actually find that you will find 2 ups and 2 downs. Okay. And in reality anyway there is a little bit of clock to queue delay. So this is the consistent solution. Okay. You won't get alternating ups and downs. So you get two ups and 2 downs and so on. Okay. So now what is the peak to peak? What is it? Yeah, it is basically with one up you are getting 2 pi ICPR KVCO times T naught, and then now you get 2 times that. Okay. Now this is important. Later we will see other implementations where the delay can be even more. Okay. So we will come to that. But what happens, let's say, for instance, just for the sake of it, this is not something that you would want to do, but we have our bang phase detector, right? This is our bang phase detector, and this is also retimed with the same edge. Okay. And our samples were there, and using this we were doing the phase detection and completing the loop. Okay. But let's say for whatever reason we do this. Okay. And we use these as basically, this is B, this is A, and this is C. Okay. We use these samples. What happens now? What difference does it make? I mean, the information we get is exactly the same, right? Because logically they are all the same. It's just delayed by 1 cycle. But what happens when you close the loop? When you do the bang this thing? So now you have 1.5 cycles of delay. Okay. So what happens to this phenomenon? What will be the pattern of up and down, you think? 3 ups? How many consecutive ups and downs will be there? Huh? Is it? I mean, think of this, what will the phase curve look like? What will be the phase versus time look like? Doesn't matter how many, I mean the shape, how many ups and downs you have, what will the shape look like? It will be triangular. So you have to decide the period of the triangle, right? And that's the easiest way to think about it. So now, okay. Now in our original case, up and down were delayed by some half plus delta cycles, right? From the relevant transition. Okay. So now let's say instead they are delayed by K by 2 plus delta. The delta represents that small shift due to clock to Q delay and so on. Okay. Cycles from the relevant transition, right? Then what do you think happens? What should you look for actually? When will you start getting down here? When are we starting to get down? Correct. So this is when you start getting a down signal, right? This is when you start getting a down signal. Now, that should be in response to what? Why will you get a down signal? When clock is leading. So that means that clock phase has to be positive. Clock phase has to be positive. So where is that? So throughout this whole period, right, you are getting a down signal, right? So now this could have come from where? I mean, this is in response to what? So here, okay, somewhere over there, okay. Is this clear? Okay. So basically, if you look at this, so let's say you get n consecutive down signals, okay. So that should be in response to n samples here which are too early, okay, n cycles where the clock is too early. Obviously, that's why if you have you should have n consecutive cycles where the clock is too early for you to get n consecutive down signals, okay. And what is the delay we have? This is the earliest case where the clock is too early, and that is what is giving you this first down pulse, right? So where will you measure the delay? How much is this delay? That will be K by 2 plus delta. I am taking a general K, okay, you can substitute it later, okay. So what next? Huh? Yeah, K by 2 plus delta cycles before, yeah, correct. So what can you say about the half period here? So first of all, this has to be an integer, right? This whole thing has to be an integer, okay. So from here to there, that is from here to there, it has to be either an integer or a half integer, okay, right? So what will that be now? It's K by 2 plus delta, but you have to round it up to the next half integer. So this will be K plus 1 by 2, okay. This is okay. So what will be how many consecutive ups and downs will you get? Well, I've already written it, right? What is it? No, I mean for this general case, when you have K by 2, I've already written everything here, right? What is there to think? K plus 1, it's just twice this, no? I mean, this whole thing is just twice that, okay? So if you are delayed by K plus 2 plus delta cycles, you will get K plus 1 consecutive up and down, okay? So when K was 1, that is you are getting half plus delta, you are getting 2 consecutive ups and downs, okay? Is it okay? So in this particular case, what happens? The way I have shown it, what is K here? K is 3, okay? So you will get how many? 4 consecutive ups and downs, okay? Is this fine? So the more delay you have in the loop, the more you have of this bang bang jitter. So this is specific to the bang bang jitter, right? This is not something that would happen with a linear phase detector. But I mean, this you can imagine. Let's say you had a heater or a cooler in a room, and you don't really turn it on and off based on how you are feeling now, but maybe like 5 minutes earlier. So for 5 minutes, obviously it is continuously cooling or heating beyond the requirement, right? So when you have bang bang loop, when you have this binary type detection loop, what happens is the longer you delay, the longer you have latency in the loop, the more latency you have in the loop, the more the error will build up during that time, right? And that's exactly what's happening here. So the more delay you have, the more this phenomenon. So remember, in this case, I don't have any noise in the system. I am not considering any noise. The input data is also jitter free. It is just that the bang bang action is what is causing this much jitter. Is this okay? So this is something specific to the bang bang phase detector, and it also depends on the latency. The relevance of latency will become clear later, because sometimes especially it will be important when we go to completely digital implementations. Okay. So these up and down pulses will be at a very high frequency, right? In fact, the same rate as the data. When you complete the loop digitally instead of through analog style, okay, so you will not process the digital data at that frequency, certainly not at 10 or 20 gigabits per second. You will deserialize the data. You will implement the same logic. You can implement A XOR T and B XOR T, but instead of doing it in one stream at 10 gigabits per second, you may do it in 16 parallel streams at 625 megabits per second. That is what is easy to implement in digital circuits. But this process also involves a delay. Okay, you can imagine that if I have this process of deserialization, we haven't gone into the circuit level details, but even without knowing anything, what are we doing with deserialization? So let me consider just 4-way deserialization. Okay, what happens is, this is the input, and the output there should be like 4 streams, which will be 1, then 2, then 3, then 4. Now if you have to line them up like this, you have to wait for the 4th one to come before you line up, right? So for the first one, there is at least a delay of 3 cycles. Okay, so the more you deserialize, the more number of parallel streams you have, the more delay you have. Okay, so you can now see that the latency in closing the loop can be quite large, right? Because if you deserialize by a factor of 16, you will have at least 15 cycles delay, and then maybe some more delay for computing the logic, and then you return this. So that amounts to a lot of delay, and that will give you this type of triangular phase. Okay, so what is happening here? This is, the clock is alternately becoming early and late and so on, and this peak to peak value, this is what is known as bang bang jitter. Okay, so what we saw is that bang bang jitter with jitter free alternating data input. Okay, what is that? This will be, how much was that? You will basically build up the phase for this many cycles, right? Is 2 pi ICPR KVCO times K plus 1. Okay, this is correct, no? So this is the peak to peak bang bang jitter. If there is a delay of K by 2 plus delta cycles between a transition and the corresponding up or down signals. Okay. So this is what is known as bang jitter. Of course, you can express it in radians, you can also express it in UI or seconds or whatever. Okay. Oh yeah, sorry. This is this here. This is the amount of phase drift for up in one cycle, and if you have it for k plus 1 cycles, you will go by so much. This is the peak to peak value. Okay. And this depends on the latency. Okay. Now, how would you minimize this? What do you have to do to minimize this? Huh? I just look at the expression and tell me. Current. So basically, it is, so this is fixed and this latency is also fixed by the architecture. Let's say you also minimize it. Okay. It basically depends on this product, ICPR, KVCO, right? Now, if you can reduce this product, you can reduce any of those three, right? It's all the same. To reduce the bang jitter. But what else? Where else do you see this product? Huh? Bandwidth. What is omega U? Density factor times ICP or KVCO. That's all, right? I mean, you have 2 pi KVCO cancelling with a linear phase detector. So here it will be for a bang phase detector, it will be the effective KPD, density factor, and effective KPD, which depends on the jitter, times uh, 2 pi ICPR KVCO. In any case, the bottom line is, if you try to reduce this product, you also have to reduce the bandwidth. Okay. So there is again a direct trade-off between, big trade-off between the jitter. This bang jitter is part of the jitter generation, right? Essentially, if you feed in jitter-free data, you will still get jittery data. Now we are saying that even if there is no random noise in the system, okay, no noise in the VCO or the charge pump or the resistor, you will still get this jitter. And if you try to reduce this jitter by changing the loop parameters, you will also end up reducing the bandwidth. Okay, so that can be a serious trade-off. So that means that you can't increase the bandwidth too much. You may want to be able to follow the jitter in the data and reduce the jitter of the jitter contribution, random jitter contribution of the VCO. But the bang jitter will start increasing, okay, and will become dominant. Okay, please think about this, and this issue of latency will become important later with digital implementation. So next time what we will look at is the digital implementation of the clock and data recovery. Yes? Latency is basically this delay, the delay between, so latency refers to essentially delay, that is you are sensing something now and the result comes out some amount of time later. So now this latency, if it's an open loop system, right? So then you just have the delay and you have to look at whether the delay is acceptable to you or not. Okay. So for instance, I mean, you write your quiz and then you get your marks after some time. So that is latency. Now, if you're only looking at the marks and not doing anything about it, okay, the delay is bad, but nothing happens. But if you're also looking to improve yourself, the latency had better be small. If you have to enclose it in a feedback loop, right? So then, if I give you your quiz marks like 2 years later, what is the point? You will not be able to do anything with it. Okay. So this, the latency is particularly important for feedback correction. And in general, you will see this. You would have seen this in analog IC design also. The more the latency in the loop, the slower the feedback has to be. The lower the bandwidth has to be. That means that you cannot correct for rapid fluctuations. Okay. Because for the feedback loop to be stable, you have to reduce the bandwidth if the latency is too large, because you know that you are only going to react to something that happened so long ago that you have to make any changes rather gently, which is now equivalent to reducing the bandwidth of the loop. Okay.